Okay, so we're going to work on an example of solving a separable equation that's actually an application problem. And this problem is going to be about Newton's law of cooling, which is given by d capital T over d little t, where big T is temperature, little t is time. So that's change in temperature over time is given by some constant times T minus T sub r. So there's some sort of scaling for how this change occurs, but it depends on how far the current temperature is from TR, room temperature. And then here I've already written out the word problem. I'm going to read it to you, and if you want to write it in your notes, you might want to hit pause and do that. But the problem we're solving is when a cake is removed from the oven, its temperature is T equals 300 degrees Fahrenheit. And then after 3 minutes at room temperature, which is T sub R is equal to 70 degrees Fahrenheit, the cake reaches temperature 200 degrees Fahrenheit. And so our initial value problem from the word problem is that we need to find a differential equation, which is Newton's law of cooling, and we need to find an initial condition. Where little t and big T are going to be time and temperature. So our Newton's law of cooling is K times T minus T sub R. And in the problem, we're told that T sub R is 70. So I'm going to go ahead and plug that in. So that's Newton's law of cooling for this room and the cake in that room. And then our initial condition should tell us temperature at the start of the problem. And so our problem starts when we remove the cake from the oven. So I'm going to call that time 0. Nothing has happened yet. And then the temperature of the cake when it leaves the oven is 300 degrees Fahrenheit. So T of 0 is going to be equal to 300. Big T temperature is given in degrees Fahrenheit here, and little t for us is going to be in minutes since the cake left the oven. So T equals 0 is when the cake leaves the oven. And then we can plug in 3 to be at 3 minutes after the cake left the oven. So in order to get a solution to this problem, we want to understand how the temperature is changing over time. That seems to be what this is about. If we solve for T of T, we could know the cake's temperature at any time and know when it's safe to apply frosting. But in order to do that, we need to find K. Because right now, I don't know what K is, but I have some extra numbers I haven't used yet. I know that after 3 minutes, the cake's temperature is 200 degrees, so somehow I should be able to apply that to find K. But first, we're going to have to go ahead and solve our initial value problem using the separable equation method. So this equation is separable because I have something that depends on big T, and then this K is sort of our constant function that depends on little t. So when I rearrange that, I'm going to get dt over t minus 70 for big T is equal to k d little t. That's just moving the same variables to the same sides. And then we go ahead and integrate, and we're going to get some more natural logs out of this. You'll see them a lot this section. So integrating 1 over t plus 70 with respect to t gives us natural log t plus 70 plus an unknown constant. And then integrating k with respect to little t gives us k times little t plus some different unknown constant, which I cannot call k, so I will call h. Yep, h is not used here, so I'm safe. And I'm sorry, when I integrated just now, I wrote t plus 70, but that's definitely t minus 70. Integrating does not change that denominator when you put it inside the natural log. So I've successfully integrated everything. It's going to help me to solve for big T because everything is in terms of temperature here. So I've got that T minus 70, natural log of that would be equal to, I'm just going to use the C tilde for being like H minus C put together. Or T minus 70 is equal to E to KT plus that C tilde. And I'm going to move up here to keep rearranging things. That means that T is equal to 70 plus E to KT plus C tilde. And I'm going to do that thing again. Where E to KT plus C is E to KT times some unknown constant. That's just going to be a little bit easier for all the algebra we do when we plug in initial conditions. So I would say this is the version of T that you want to say is like its final form. And then next, we're going to go ahead and plug in our initial conditions because we know those values and it's going to help us clear up some of the unknown constants in the equation so eventually we can solve for that k that we're wondering about. Oh, I really didn't want to use k's, I'm sorry. I will call it h tilde. Okay. So we know that t of 0 should equal 300. So we should have that 300 is equal to 70 plus that unknown constant e to k times 0. And just so you know, e to 0 is 1. So that's just 70 plus h tilde. And in your skeleton notes, I'm calling that C1. I am so sorry. I only just saw it. But that's going to be 300 minus 70 is T30. So this is all looking like a bit of a mess, but it's going to start, ooh, sorry. Hit pause if you're still writing so that you can finish up this page. But this is all looking a little bit messy, but as soon as we start plugging numbers in, it's going to get a lot easier. So the solution is T is equal to 70 plus 230 e to kt. Now that we were able to plug in that unknown constant, there's only one thing that's missing from this equation. We don't know what k is. So there's more information from the word problem that we haven't used yet. If we go back, we see after 3 minutes at room temperature, the cake reaches 200 degrees. So we should have T of 3 is equal to 200. If we plug in 3 minutes, we should get temperature 200. Kind of the same way we work with initial value problems, but now instead of solving for that unknown constant of integration, we're solving for this unknown k in Newton's law. So this is going to give us that t should be 70 plus 230 e to kt. So when we think about at little t equals 3, we're going to have 200 should be equal to 70 plus 230 e to k times 3. That means that e to 3k is equal to 200 minus 70, move that over, divided by 230, which is 130 over 230, or 13 over 23. We're trying to isolate k, so we're going to take natural log of both sides to undo e, just like sometimes we take e to undo ln. Oops, I definitely want to plug in that simplified version over there. So what we're going to get is that k should be 1/3 natural log 13 over 23. And that's going to be approximately minus 0.19, I wrote in my notes. So the solution is, the temperature is 230 e to minus 0.19 t plus 70. And then I know the video is running a little bit long, but I do just want to talk about the behavior we're seeing right now, so that the next video is sort of like its own thing. But if you need a quick break, go ahead and take one. I know that there's a lot we've written on this page that you might want to pause and catch up with. But I'd like to know, as time goes on, what happens to the temperature of the cake? So it's the limit as t goes to infinity of that thing. If it's been a while since you took limits, it's okay. But basically, e to negative exponent goes to 0 as t goes to infinity. So as time goes on, the temperature approaches 70, which is what we'd expect. That's room temperature. Our intuition is things at room temperature go to room temperature. You might remember that limits are like not actually reached, though. So what we're seeing is that the solution is going to t equals 70. And places that solutions go are equilibria from the prior section that we covered on equilibria. And in fact, if you went back to the differential equation, you could solve for the equilibrium and know that it's t sub r equals 70 before you even got to this point. But we should note that the solution never reaches that value. So all our discussion of equilibria were that we tend towards those values, but I do want to be clear that mathematically that E doesn't actually go away in finite time, so it's just forever heading towards that value. So that's it for this application problem. Hopefully it was fun. You got to think about cake for a little bit. And in the next video, we'll talk a little bit about definite integrals and initial conditions.